Lena, thank you so much for those kind words, that very warm introduction. So it's a real pleasure to be here. As kind of Lena mentioned, really the thing that brings me most joy is working with all the really phenomenal students, not just in my lab, but just across the departments and colleges here at Carnegie Mellon, and also the wonderful staff. I mean, I've had starting with during the pandemic and over Zoom, working with Lena, and also prior to that, working with Anita in terms of some of the translational work that we've been doing in terms of getting some of our work out of the lab into the commercial space. So I want to start with just a picture of the current lab. It's a very diverse group, in terms of researchers coming from all different backgrounds, disciplines, career objectives, starting very early on in my career, being an academic, having always done my research in kind of these academic labs, I thought coming to Carnegie Mellon, I'd create a lab of my own, and I would train people to become professors, folks just like me. What I learned, though, very early on, even with that first cohort of PhDs, is that, yes, while there's still a lot of interest in getting a PhD to have a career in academia, more and more students wanted to go into entrepreneurship and launch startups of their own. And really, that's what they found to be the most rewarding way of really putting what they learned at Carnegie Mellon into practice. And so one of my first PhDs launched a startup. This is back in, I think, like maybe 2015. I didn't participate in that. He took a lot of his PhD work on wearable sensing and wearable computing and decided now to apply that to agriculture and launched what continues to be a very successful company kind of in the agricultural sensing space. I was still kind of early in my career at that stage. I didn't choose to participate, but then I kind of saw the trends. More and more other PhDs, postdocs, they really weren't satisfied with that traditional academic route. Still a lot of other students would go off and become faculty members, and some of them now have, students who are faculty, so there's kind of these academic children and grandchildren. But I guess the children I've been most kind of engaged with over the years have been the ones who decided to pursue the entrepreneurial route. And I'll kind of go through, some of those endeavors in a bit. First, though, I just want to give a little bit of context for what I do and how we got to where we are in terms of our entrepreneurship and commercial translation. The research that I do in my lab, we're called the Soft Machines Lab. Our work is what I would define as soft matter engineering. Right, so we're based in the Department of Mechanical Engineering, but we don't work with traditional engineering materials in terms of how we build robots and machines and, say, computing systems. So whereas traditionally you would use materials like steel and ceramics and semiconductors, typically fairly rigid materials, what we decided to do in my lab, and we were one of the first internationally to start pursuing this, was to look at the completely other end of the spectrum in terms of materials and their makeup and their mechanics, and start thinking about engineering robotic systems and computing systems out of fully soft and deformable materials. And the reason is somewhat intuitive, right? Because if you look at engineered systems, yes, these are all kind of, hard cased for the most part, bulky, rigid, very load-bearing type systems. But if you look to nature and to biology, for the most part, functionality is achieved with entirely soft and deformable systems. So as we start thinking about technologies, computing systems, robotics, human-machine interfaces that start making physical contact with the human body or with the natural environment, we really have to start re-examining the types of materials kind of at a fundamental intrinsic level that we use to engineer these devices. And so that kind of figure that you see there to your right is basically how do we take kind of rubbery materials, soft materials, fluids, gels, granular matter, and get them to have the functionality of more traditional packaged electronics and robotic hardware. And so that kind of leads to these different research thrusts within my group at the Soft Machines Lab. Biology is a big source of inspiration for us, and so a lot of the work we do is in the space of bio-inspired soft robotics. Now, when we think bio-inspired, we're not talking just about building a robot that looks like this snail or looks like that brittle star. It's also about thinking about the makeup of these robotic systems, the types of materials, the artificial muscle, right, like the actuators that would be alternatives to motors, the artificial nervous tissue, the artificial skin. How do we kind of move away from these existing paradigms in engineering and robotics and really start putting materials at the center of how we re-examine and re-engineer these systems? A lot of the work with the artificial nervous tissue, artificial skin, these kind of soft and stretchy circuits and sensors naturally blends into wearables, wearable computing devices, human-machine interfaces, and of course, the underlying all of this is the need for new advanced materials that can achieve all the same kind of electronic or actuator or motor functionality of traditional engineered systems, but also still match the compliance, the elasticity, the deformability of natural biological tissue. So it's fairly sweeping, and so that's kind of why we have such an interdisciplinary and diverse research group here in my lab. I'll just very briefly go over these. I don't know if these videos will run. Oh, there it goes. So these are the robots in action. These are all real-time videos. And so quite slow, but at speeds that are relevant to natural biological systems. So you can see here is that there's quite a lot that we can do with some of these more advanced materials that we use for the artificial skin and artificial muscle. Here on the your right, you see that snail. We have a little kind of electrical circuit that's self-healing. We cut it, we can stick it back together, and it doesn't really interrupt too much the natural locomotion of these bio-inspired robots. That bottom right figure there is actually showing a soft robot that was inspired by a echinoderm that existed 400 million years ago. And it was actually the ancient ancestor to the brittle star, that starfish that you see on the left. And so by expanding the range of materials that we use in kind of robotics and machines, we can not only replicate kind of modern day organisms, but actually go back in time and start resurrecting organisms that have been extinct for hundreds of millions of years. Wearable skins, again, let's see if these videos run. Okay, it looks like we're fine here. These same soft electronics and sensors can also be used kind of within a wearable context. I'll talk about Life4 Labs that Lena mentioned, one of the first startups that I was involved with as a spin out from the group that looks at basically electronic stickers that can adhere to the skin. They're fully wireless, capable of multimodal sensing so that we can collect all sorts of health vitals and physiological information that can then be transmitted wirelessly. Another initiative, this is actually a collaboration with Meta, is actually specifically Facebook's AI, so Meta AI's group on using some of these novel materials for basically tactile skins in robotics. So giving kind of more conventional robotic end effectors and dexterous manipulators basically a sense of feel and touch. And I'll kind of touch on, no pun intended, touch on that again when I get to the end and talk about this new ERC initiative that Lena mentioned that we were recently awarded. And then lastly, the last research thrust before I kind of get into our startups is in the space of soft multifunctional materials. So all of these innovations in robotics and in wearables and human-machine interaction, even haptics, really depends on not just advancements in AI and computer vision and sensing, but also new types of materials that can enable all the types of functionality that we need for basically motion and sensing and electronics, but also have these form factors and kind of mechanical properties that again mimic natural biological tissue. All right, so this leads me now to our spin-off efforts, and this is something that started about, I'd say, 7 years ago, 8 years ago, in terms of really making a more a deliberate effort to kind of get these efforts off the ground, and I really want to quickly note that really critical to getting a lot of this work out of the lab and into the entrepreneurial space and the startup space. First and foremost were the students themselves, the PhDs and postdocs who weren't really satisfied with just seeing their research and all of their work and all their effort that they toiled over just basically begin and end in the lab. What was most rewarding for them was to actually see it be adopted. And what they all learned, and what I learned quite a bit, the hard way as myself, a PhD student and a postdoc, is that you can come up with brilliant ideas. These ideas can be really innovative. They can have high performance, really, outperform whatever exists kind of in the commercial space. But really, nobody's going to care so long as it just stays a research publication, or it stays, say, just a patent that sits there within the university's patent portfolio. Unless we're aggressive in partnering with companies early on to get these patents licensed, then really it's on us. We as the inventors kind of have that burden of starting the company and commercializing, and really basically teaching the wider community of how these kind of technologies can find value in the marketplace. And so that's what we decided to do. So instead of just trying to sit back and wait and hope that companies would be interested and start licensing this IP, we decided that we were going to license the IP back to ourselves and launch these 3 spin-offs. And so I'll talk about these each, Arieka, eStat, and LifeWare that we just mentioned. But I also want to talk about 2 other critical pieces. So first and foremost, it's the researchers themselves who take that lead role and become the CEOs and co-founders of those companies. It was folks like Anita in the Tech Transfer Office who helped us actually create this IP portfolio that was really vital to the success of these startups. And then the whole kind of ecosystem, the support system that we have here at Carnegie Mellon and also within the Pittsburgh region. Short Center for Entrepreneurship, Project Olympus, at the time that the NSF, National Science Foundation I-Corps program that had programming here at Carnegie Mellon, and also for us, Alpha Lab Gear was a really kind of vital partner in terms of incubating and accelerating a lot of this, and then later on we can talk about some of the angel investors and VCs who also later played a vital role. But in terms of kind of really getting off the ground, it was really all those 3 things, those 3 pillars: the tech transfer, the inventors and co-founders themselves, and then also these accelerator incubator programs that end up being really kind of vital. This is from last Christmas lab party, just to give you a sense that some of these faces are folks, myself included, kind of in the far right there. Some of these are folks from the lab. But then there's all sorts of other students from across the country who came here to Pittsburgh to take part in these initiatives. Another kind of key point I want to make here is that I would say Pittsburgh, thanks not just to the universities, but also to the companies and to the basically just the region and just the kind of the environment that we have here, is a very attractive place for young people, undergrads, master's students, PhDs, postdocs, especially folks kind of in the early stages of their career who have mobility. They will choose Pittsburgh over most actually other cities of this country, and then they will kind of even choose Pittsburgh, say, over other larger markets as well, because of all the attractive kind of qualities that just living in Pittsburgh has, in addition just to this vibrant ecosystem that we have that's spun out from the universities. And so we've had actually no problem in terms of recruiting students and even poaching folks from the Bay Area and some much bigger companies and more high profile companies, because they're very excited to make an impact with a startup here in Pittsburgh. So I just wanted to kind of mention that. And you notice also it's a fairly young group of folks kind of involved in all these startups that we, this is all from the holiday party celebration. So not fully inclusive of everybody at the companies, but kind of gives you a flavor of the folks working with these three startups. So I'll just kind of quickly go over these. So LifeWare Labs was the first of the spin-outs. It was officially launched in 2018, although we had some STTR funding and SBIR funding that we were awarded just the year before, and that was kind of our trigger to get started. I will note that LifeWare Labs never did take on VC funding. They've always supported themselves through non-dilutive government grants. And the reason for this is that it was and it remains the priority of Life for Labs to create these kind of soft electronic stickers that are clinical grade, that can be used kind of within a clinical setting, used by hospitals, used by patients. And so we're really aiming here for FDA-approved products, something that VCs and angels kind of early on didn't really necessarily have a stomach for, but something that the Department of Defense really saw kind of a vital need, especially when it comes to monitoring health vitals, say in say remote environments or in scenarios like combat casualty care. I'll just quickly play this video here showing kind of one of those use cases. Hopefully the volume's not too high, but this is just a kind of a promotional video that Life4 put together last year to basically market their products, basically to their number one customer, which is the U.S. military, U.S. Army, Air Force, Marine Corps, Special Forces, and you can see, this is a combat casualty situation where you don't have the luxury of just parking an ambulance right there, kind of on site, right, or necessarily even bringing a helicopter, medevac in immediately, and so it's helpful to have something with a small sticker-like form factor that has all of the embedded electronics needed for kind of doing triage and detecting basically the severity of injury and knowing basically how urgent it is to evacuate a casualty. The next half of this video is going to show you basically a civilian use where these same technologies could be used in say, first responder care as well. Even in cases where you can get an ambulance, still there's value in having something that adheres to the skin and is mobile. So that's Life4 Labs, and I'm going through these rather quickly. Happy to also chat kind of offline with folks interested in learning more about any of these companies. I can always connect you to the co-founders. Orieka is an advanced materials startup. A lot of the work that we've done is, as I mentioned, focused not just on the end product in terms of the robot or the wearable device, but also relates to the advanced materials. And what we discovered kind of along the way in my lab is that there's tremendous performance kind of advantages when you kind of take kind of rubbers and elastomers, materials that are commonly used in engineering, and blend them with metals that are liquid at room temperature. So basically you have basically these rubber metal blends that have all the kind of the same elasticity as rubber, but then the same thermal or electrical properties of a metal. So that's a pretty unique thing that we discovered in the group, kind of one of our most important scientific discoveries. Orieka is a spin-off company that was launched to kind of commercialize that specifically as a thermal interface material. And I can kind of talk later about some of the successes and also challenges with trying to get these materials out of the lab and actually into products, smartphones, laptops, servers, all sorts of computing devices that produce a lot of heat because of their power requirements, and materials like these thermal interface material rubbers, timber as we call it, seem to outperform kind of existing kind of commercial products. And then the last company I'll mention here is eStat Actuation. Also kind of a materials-centered type startup company where this builds again off of PhD thesis work on a electrostatic adhesive clutch that uses these thin film dielectrics that we developed in the lab. And we have this ability basically to have a very high load-bearing state, as you can see here, but then we can turn off the clutch and then it suddenly becomes freely moving and allows for basically freedom of motion and say a mobile robotic or wearable type device. Now, what distinguishes this clutch technology from anything else out in the market is that it is orders of magnitude lighter and requires also orders of magnitude less electrical power input in order to basically maintain performance. So here's in the off state, you can see it kind of moves freely. Then when it's in the clutched on state, it can take very high load, even impact loads. And it does this with just milliwatts of electrical power input. So much more efficient, much more lightweight than the kind of the standard motorized clutches. So I'll just end here with the two slides that actually touch on initiatives that Lena had mentioned. So one is the Softbotics. that basically is about putting materials at the center of how we design robotic systems, human-machine interfaces, and just kind of looking at autonomy in general. So this is a initiative that was launched by the College of Engineering a few years back, during the pandemic. So kind of a lot of those early meetings were on Zoom, and there's been a lot of investment, not just in terms of infrastructure with the new Scaife Hall building and all the labs, but also in terms of from outside, in terms of kind of funding opportunities. The NSF Hand ERC is one such initiative where we've gotten investment. This is $26 million, although it's renewable for an additional 26, so $52 million over the course of 10 years. There's partnerships with other universities, and it actually does, I mentioned touch and hands and, and being able to kind of augment sensing capabilities and robot end effectors. And that's really the goal here of this new hand center. And what I also want to kind of, and I'll close with this, is to really highlight the really critical involvement of companies, both large and small, in participating in the innovation ecosystem for this hand center. And that really is what's going to be vital in terms of getting that work out of the lab and into the marketplace and have true impact. So I'll end it there. So thanks so much. Perhaps we have time for questions. Take one? Okay.
Anyone have questions?
Thank you.
Hey, thanks for a great talk. Actually caught your talk at WIST as well in the workshop on Sunday. I'm curious how it, except for these more narrow applications of soft robotics, how do you think that soft robotics might weave their way, no pun intended, into kind of the next mainstay computing platforms that, right now we mainly use rigid devices or screens in everyday life. How do you think we might evolve into a society where, soft materials might enable this sort of ubiquitous computing vision that's been around for so long?
So one of the biggest kind of centers of activity that we've seen kind of in the commercial space and with our kind of company partners has actually been more in haptics, augmented reality, VR. And so, there is a strong interest by groups like Meta Reality Labs to, not limit basically all that functionality to a headset, but now distribute all that sensing and also kind of tactile and haptic feedback over kind of different parts of the body, over skin, and incorporating that into garments and stickers and gloves and all that. So that's where we're seeing kind of the most activity. And I would think that in the kind of computing space, wearable computing space, that's where we're going to see probably the biggest impact, so haptics. And that's certainly our own research, that's where it's also kind of headed in that direction.